This tutorial shows testing the requirements, the calculation and interpretation, as well as reporting the results for the one-sample t-test in R. The one-sample t-test is used when you want to test for a difference between your sample mean and a hypothesized mean, i.e. population mean. For instance, I have a sample with 51 observations and want to test the mean of the IQ against the average value of 100. Required are a dependent variable on an interval or ratio scale and an approximate normal distribution of this variable. First, you can conduct the Shapiro-Wilk test. Its null hypothesis is that the variable being tested is normally distributed. You can use the Shapiro.test function in R and within it your test variable. For example, the variable IQ of my data frame df. If the p-value is below a predefined threshold, you have to reject the null hypothesis of normal distribution. This is not the case for my IQ variable. Please be aware though that with larger samples, the power of the Shapiro-Wilk test increases, and negligible differences will lead to a rejection of a normal distribution. Information on that phenomenon can be found in the sources in the video description. Second, an ordinary histogram can be used to test for normal distribution. Simply put the test variable within the hist function. What you are looking for is an approximate bell shape of the column heights. Note that there may be small deviations that will not hurt the assumption. In my case, minor deviations exist, but I can still assume a normal distribution. Third, a QQ plot can be used. In order to plot it, you put the test variable within the QQ norm and subsequently the QQ line function. The dots represent the observations and the line the perfect normal distribution. Therefore, the distances between the dots and the line should be minimized. Again, there will be acceptable deviations, especially on the edges of the distribution, meaning the upper right-hand corner and the lower left-hand corner. If you cannot observe an approximate normal distribution, you should use the one-sample Wilcoxon test instead of the one-sample t-test. As a first step, I want to see the mean of the IQ variable for my sample. The mean function provides that answer, and the average IQ is 109.8. I now want to see whether that is significantly different from the population mean of 100. For this, I use the t.test function and start off with the test variable, the IQ. After that, I use mu equals 100 to test my sample mean against the population mean of 100. Note that the default testing will be two-sided, meaning you test only for a difference. In case you proposed in advance that your sample mean is larger than the population mean, you can add the argument alternative equals greater, meaning your sample mean is larger than the population mean. If you, however, hypothesized a smaller sample mean, you use alternative equals less. I can now run this one line and get the results. If the p-value is below the predefined threshold, for example 0.05, the null hypothesis can be rejected. Reminder, the null hypothesis of the one-sample t-test assumes no difference between sample mean and population mean. In my case, I defined alpha as 0.05 and can therefore reject the null hypothesis, because my p-value for a two-sided test is 3.027 times 10 to the negative 6, so it's extremely small. My sample mean is therefore different from the population mean. If I did a one-sided test for a larger sample mean than the population mean, I could certainly see that result as well. The p-value would be half of that what I see in the two-sided test. After a significant one-sample t-test, the effect size should be calculated. The first step is installing a new package called LSR, using the install.packages function and library function. Please note, only use quotation marks within the install.packages function. The second step is using the Cohen's d function, which obviously calculates Cohen's d. The test variable and the hypothesized or population mean have to be entered into this function. The syntax is the same as for the t.test function. After running this line, you will only get one number as output, Cohen's d. The third step is to classify the magnitude of this effect. If similar studies in your research field exist, compare your effect size with the given ones. If no comparable study exists, use the common thresholds within your research field. If those are also non-existent, you can refer to Cohen 92, a power primer. Page 157 shows 3 thresholds for the one-sample t-test. If your Cohen's d exceeds 0.2, it is a small effect. If it exceeds 0.5, it is a medium effect, and if it exceeds 0.8, it can be classified as a large effect. When you're done, you have to write up the results. First, one formulates whether the sample mean is different from the hypothesized mean or population mean. For this purpose, the t-value is reported together with the degrees of freedom. In this test, the degrees of freedom is always the number of observations minus 1. This is followed by the p-value, and in the case of a significant difference, i.e. effect, Also, the calculated effect size Cohen's d. Finally, the magnitude of this effect is classified with, for example, Cohen 92 or the respective research field specific thresholds.